To the final session of today, which will be the talk by Sam from the University of Edinburgh on effect handler oriented programming. Sam.
Yes, right. Thank you very much. Yeah, I'm Sam, and I'm going to talk about effect handler oriented programming, which is also the title of a research project that I'm working on for at least 4 years, funded by the UKRI. So yeah, I'm happy to be here and being able to tell you about this. But before I get on with the main talk, I'm going to start by asking you a question. You've been very good at asking questions of the speakers. And I want to ask you, what is an effect? Does anyone have an answer to this question? Go for it. The thing that you want to achieve, a state transition. Okay, can we have anything produced by the program that is not the result? Did I have, was there another?
You don't get a value back.
You don't get a value back from an effect. Okay. Yep. Any change that is not determined by the syntax of the program? That's too specific. Okay, that one's retracted. Any more suggestions? A unit of impure computation. James?
Anything that violates referential transparency.
Anything that violates referential transparency. Is this one at the back? Or you just... Sorry? I couldn't hear that. Could someone else?
Anything that arises from a cause.
Anything that arises from a cause. Cause and effect. Yes, wonderful. The computation you want to do.
Yes.
Okay. Some interesting answers here. Yeah.
The combination between an exception and a computation.
A combination between an exception and a computation. Right. Have you been reading about effect handlers? So. Yeah.
Some kind of communication with some kind of environment, like abstract.
Some kind of communication with some kind of environment. Yeah. Okay. All right. I could maybe just go on like this for 45 minutes, and then we could finish, and that would be fine. Yeah, we're done now. And in fact, yeah, I'll say I'm going to give you a sort of high-level overview of effect handlers and give you some kind of an answer to my perspective on what effects are. But I'm quite happy to stop at any point. So just tell me to stop when we run out of time. That's fine, and I'll just wrap up. Okay, so that was an interesting range of answers. So my perspective is with sort of classical theoretical models of computation, we might view a program as just a black box. It just has inputs and outputs. So this is a pure program, and this has lots of benefits to view programs in that way. And I guess the kind of lambda calculus models that James was presenting could be viewed in this way. But it misses out on a lot of what we care about when we're reasoning about real-world programs. I mean, in fact, all of the stuff that these C programs that Susmit's been showing us are very much not of this form. And yeah, generally programs need to interact with their environment as well as maybe computing some result. And typically they don't talk straight to the outside world. They might go through some runtime system or operating system. Oh yeah, I've got this thing, haven't I? So I can wander around. So I would just refer to any of these forms of interaction, either with the outside world or with maybe some other part of the program, as effects. Anything, I think someone did say something along these lines, anything that isn't about just computing that final result value. So I have these whole lot of examples here: I/O, concurrency, distribution, exceptions, even things like choice or probabilistic programming, as Ohad told me to say all the controversial things while he's out of the room getting coffee. I'm not sure I have anything particularly controversial to say, except that all of the stuff, the probabilistic programming languages can also fit into this framework. Now, in typical mainstream programming languages like C, these features tend to be just sort of built in, hardwired, and difficult to reconfigure, customize. Oh, I was just insulting you. Oh, sorry. Not really. And in particular, yeah, one of the examples I focus on is the web application domain. Think of JavaScript. It has a number of different kinds of, well, asynchronous programming or concurrency features. So there's generators, for instance, there's promises, async await, and each of these things is implemented separately, and you can't really change the behavior of it. So it's a pain to kind of maintain these things, even though they're doing quite similar things. And this is where effect handlers come in. So they're based on the theory of algebraic effects, and they were introduced by Gordon Popkin and Mattia Pretner. And originally in a very abstract categorical setting, but I'm going to give you a very high level perspective from the point of view of programming with effect handlers. And I'm not going to say very much about algebraic effects, although there's a connection here. So crucially for programming, effect handlers are composable and customizable, and we can define them inside our programming language. Yeah, at this point, I'm just going to sort of flip back to this question of effects, something I haven't sort of captured on the slides, but is actually an important distinction to make, is that there are, well, I guess it comes down to this perspective of, well, we're interacting. We may be interacting with the outside world, so I call those external effects, or we may actually want to be interacting with some other part of the program in such a way that the overall behavior of the program is it still just takes an input value and produces an output value, but for convenience, we might want to write it in a particular style, like we might want to simulate some form of concurrency or writing to memory or whatever. And that's what I call an internal effect. So in particular, effect handlers allow us to define effects inside the programming language. And that will become much clearer very soon. The important tool that handlers provide in order to be able to do this in a very general way is they give you first-class access to the context itself. Again, I'll explain what that means when we get to the examples. But if you're familiar with other things like resumable exceptions or monads or delimited control, these all have this same feature. And you can think of the interactions we're having between as being between the computation you write and this context. I think it's also worth saying that this is not just a theoretical thing. There's lots of active work in academia on effect handlers, but there's a lot of industrial interest as well. So they're deployed by GitHub, for instance. Whenever you do a pull request, it's running a library, semantic library, that makes essential use of effect handlers in order to generate the code navigation information. Also, React does not directly use algebraic effects or effect handlers, but it's many of its abstractions are directly inspired by them. And then, yeah, Uber's Pyro language does build in effect handlers, and they're used for abstracting over different forms of statistical inference. Okay. I'm going to now show you another little picture. This is an illustration of one particular view of effect handlers as kind of little mini user-defined operating systems that you write inside your programming language. So if you take the program there, we can expand that out. If we want to write it in a using effect handlers, then that top box up there, that would be our program. And we write that program and it has various effects, which I'm denoting with these. Well, these are the interfaces to our effects with these different shapes. And then what a handler does is it handles some particular effect or some collection of effects. And it can handle one effect in terms of another one. And you can have a whole stack of these things. Some of them can be, this is a pure one, it doesn't have any effects. And then some of them might actually perform effects that actually go to your operating system. So go out to the outside world. So you can imagine this, you can plug these things together in all kinds of different ways to compose your programs. This is all quite abstract. Now let's have a look at a concrete example, non-determinism. So the first thing we do when we want to program with effect handlers is we define a signature of our effects. So you can just think of these things, these are just operations. You can think of them as being rather like functions. That's the way we use them in our program. So we have one operation, choose, that takes no argument, it takes a unit argument and just returns a Boolean. Another one, fail, it takes unit and returns something of the empty type. It doesn't actually it can never return a value because there are no values of the empty type. You can think of this one as being like an exception, and this one giving us a non-deterministic choice. And I don't have this on my slides, but I'll mention at this point, algebraic effects are given by a signature like this, along with some equations as well. We don't need the equations here, although if you want to reason about these things, then you do. Okay, so we've got this effect signature, and now we can write programs using it. And I've got a whole load of stuff here to explain. This is a slightly contrived, silly example I like to use. It's my sort of starting example for effect handlers. So imagine tossing a coin. Here's a function that describes a coin toss. We just run choose, and if it's true, then return heads, else return tails. But we might have a drunk person trying to toss a coin. So I don't know. I guess I'll be that drunk person. And if I'm lucky, I'm drunk, I managed to, no, I'm drunk, I didn't, I dropped the coin, so there's no result there at all. That's what is happening in that fail branch. I've stuck absurd around there just to, so that's the eliminator for the empty type. It says if I have a value of the empty type, then I can treat that as being of any type at all. In particular, toss is what I need there. False implies everything. Okay, and then there, I managed to catch it that time. That corresponds to the other case. So this first choose was determining whether the coin was caught, and yeah, what did I get? Tails. And then the second one, whether it's heads or tails. And then we might write a program that repeats that a number of times. So the main point to take here is I've written a program. I've not told you anything about what choose and fail mean. That's what the handler is going to do. And indeed, we could write this program and then later on come along and write several different handlers that do different things and interpret this program in different ways. And that can be really useful. So in particular, if you were like OHAD's probabilistic programming scenario, you could do things like sampling, or you could tune your distributions in various ways. You could compute a distribution. Here you could compute, you could just return all of the possible scenarios that could happen here. Or you could randomly select heads or tails. I'll show you some of these too. I've also written some types here. I guess I'll explain what they mean. So these are like normal functional types, except on the right-hand side of an arrow, we get, as well as the value that's returned, we get an effect type that describes the other stuff that may happen. So that fits with one of those answers, some of the answers we heard. James?
Your definition of drunk toss
Yeah.
in the true branch. Why did you write out the definition of toss? Is that different from writing toss there?
It's the same. I just was being concrete. Yeah.
Are you drunk then?
Was I drunk? No. I think we stole the example from another paper.
So is that like exclamation mark, some sort of product?
No, it's not a product, but it is just syntax. So yeah, there are two components to a computation type, and I'll get back to this in a minute. We have the value type and the effects that happen. So here I'm just saying that it toss performs choose, and it may perform some other effects as well. Drunk toss may perform choose, and it may perform fail, and it may perform some other things. So an effect is an upper bound on an effect type is an upper bound on the things that may happen. Yeah.
So the E represents like other things that might also other effects that might also be possible, right? Like you write it just without an E and just say like it must.
Yeah.
Is that useful?
It doesn't compose so nicely, and at the moment I'm not going to talk about polymorphism. If you want it to compose, you really want some form of effect polymorphism, and that's how you do it. You just, because we might use this in a context where we want to do some other effects, and then you want to unify it with the yeah. Well, hang on, we'll come to that. All right, I'm going to show you some handlers. Well, there you go. This is a handler just for fail. Yeah, now I'm writing another kind of arrow here to indicate this is the type of a handler. It takes a computation and it gives you back another computation. So it's taking a computation that may fail, that returns an A, and we're going to interpret that as a maybe type, an optional type that might either has a value or nothing. But this fail effect has now disappeared. And this is essentially an exception handler with funny syntax. Unlike traditional exception handlers, we have this return clause, which says what to do if we successfully get a value back with a pure value. no effects. In that case, we wrap it in just of X. And then if we come across fail, we return nothing. Wait, patience. So this is just showing you how that would work. So this is just basically exception handling. Now here's an example of an effect handler that is not an exception handler. And this shows us the extra feature that we get here. So, okay, it's kind of boring. So the return clause is boring. It just returns the value. And in this case, the idea is we want to always return true from the choose operator. And we're just going to interpret the choose operator. And the extra piece of information you get on top of an exception handler, you get the effect, you get the payload, which is unit, boring in this case. We also get given the resumption. This is a function that captures the rest of the computation. And it's expecting something of the return type of choose, a Boolean. So we just pass that in, and that's the interpretation of the rest of the computation. So that's going to give us the thing on the right hand, something of the thing on the right hand side. So if you run that one on, well, it's boring value, it's boring, but if we run it on toss, for instance, then it's going to give us heads. Now the next example is more useful. This one is another handler for choose. But it's going to return a list of all the possible results that a computation may perform. So it has to be a list. So if we get a value of type A, we need to turn it to a list of type A. We just create a singleton list. And then with choose, we run the resumption twice, once with true and once with false, and we concatenate the results together. So with that one, if I run toss on it, and I get both heads and tails. Yeah, question there.
So the E on the right hand side there, that means that it's like you've eliminated this effect from the.
Yes. Yeah, so in particular, if E was just the empty effect, then this would be a pure computation. Or it takes an effectful computation and it interprets it as a pure computation. Okay. So having defined these individual lineal handlers, we can compose them together. So I'm just going to, you can compose them in arbitrary ways. You can define as many handlers as you like. And run your program in different handlers if you want. So here I'm going to run drunk tosses twice. First handle it with maybe fail. So that means, yeah, we're going to drunk tosses gives us a list of tosses. Is that right? What was its type? List of tosses. And then, but maybe fail gives us a maybe type. And then this is going to give us a list of all those things. So we get, yeah, a list of maybe tosses. And if you run this, I promise you, you get this. And what's this telling us? The first line, I think, the first two lines correspond to the case that the drunk catches the coin on the first occasion. And if they catch it on the second occasion, you can get heads, or heads, tails. But if they drop the second coin, then you get nothing. And then this is, if they get tails, then you can get heads, tails, or nothing for the second one. And then is this when they drop? Yep.
I mean, it's supposed to be this part.
Yeah. Yep. Typo, sorry. You can compose this the other way around. And hope, I don't know whether I'll get, I'm probably going to have the similar typo for type. Am I? No, maybe not. let's see, a list of lists. Yes, yeah, it should be maybe list of tosses. But in this case, because failure, well, choices gets handled first, but the failure is on the outside. Because there's some failure at some point, you just get nothing. Which, well, fits with the type. So, don't need to understand exactly what's going on with the composition of these things, but the point is that you can compose them in different ways, they all make sense, and it gives you quite fine-grained control over how you define your effects.
In the previous slide, when you defined a handler and you said something like list of toss bang E, is it saying it's a list of tosses that have the environment E, or is it a list of tosses with E? Like what's the precedence here?
Sorry, which slide?
On the return type of say all choices. It says list A bang.
That returns a list of A's, and in doing so, it may perform any effects in E. That's how effect type systems work, typically.
So the handle with taking care of weaving it through the list there.
The handle with is basic. It just applies the handler. So yeah, it takes us. So when we do if you apply all choices, it transforms the effect from having a choose to one that's the same effect that doesn't have a choose. Or it transforms a computation that may perform chooses into one that may not perform chooses, but which returns now a list of values rather than just the original value.
Yeah, but it's not just applying the function because you get a return that.
No, it's not applying it. It's not just applying a function. It matches against these operation clauses. I'm going to go into the operational semantics because this is the way to explain what it does. So I'm not giving you I'm only giving you the bits that are relevant to computations. So I'm assuming a call by value lambda calculus extended with these things. Fine-grained call by value lambda calculus, in fact. There's a rule for let, which should hopefully be obvious. And then these are the two rules for handlers. So in both of these, I'm assuming that H is defined as this thing. And in the first one, if we just have a value, then you look at the return clause and you substitute in the value for X. That's the same essentially as what a let does. And this is where all the power comes from with effect handlers. We have the evaluation context in which you perform an operation is this curly E. Well, we look at what the body of the operation clause is. We're going to reduce to that. We substitute the value for the parameter. And then we need to work out what the resumption is. That's the rest of the computation. So it's not the rest of the entire computation, it's the rest of the computation in the scope of this handler, which is essentially the evaluation context. And that's what we're binding to R here. But it's not just the evaluation context. We want to make sure, these are called deep handlers, that we handle the rest of the computation using the same handler. So you wrap handle with around the context as well. There's also this little side condition here. All this is saying is that this operation is not allowed to be mentioned in any handlers that appear in the evaluation context. So it just ensures that the nearest enclosing handler that handles op is the one that handles it. And if you think about the way in which exception handling works, it's just the same thing. Exceptions just bubble up to the nearest handler that handles them. So do effects. Question?
I was asking about what would be R in this below.
This thing. this is bound to R. Is that? Yeah. Okay. Yep.
So in the previous example, when you had the fail, it didn't have the resumption. So was that just omitted?
Yeah, that was just syntactic sugar. I was indicating I don't use the resumption. And yeah, that was, if you look at my labels on this, I've identified for 3 particular kinds of handler that are sort of interesting. If you don't use the resumption, then you've basically defined just an exception handler. Here's one where you use the resumption once, which is an important special case. And then here's one where we're using it twice. Right, good. Yeah.
Could you just achieve the same thing through training monads?
Yes.
So,
Yeah, we have a paper showing that you can encode it, but monads don't compose, and they're not very good for programming with.
If you go back to the slide with the 2 handlers, 2 ways to handle drum potters, I think that goes well.
Yeah, I mean, you could define 2 different monads. You'd have to define 2 different monads here. This is just, if you know about monads, if you know about free monads, this is just programming with free monads. The effect signature you have generates a free monad, which we then interpret using a handler. Right. Okay. Yeah.
So sometimes you have exceptions. You know, the exception handler can't handle it, and we'll rearrange the exceptions.
Yeah.
So, but here you're saying that can't do that.
Oh, you can. The type, if you're using an effect type system, you have to make sure it's allowed to be done. But you can't, yeah. If your type signature says that you're still allowed to perform the same effects, then absolutely you can re-raise it.
Yeah, like in all the sub-computations. But you said that handle it in all the.
It handles it, but can handle it by re-raising it. That's absolutely fine, yeah. There's a strict extension of exception handling, it doesn't. Oh yeah, here's some typing rules. I don't want to spend too long on the typing rules, but yeah, I guess this is the effects are just basically sets of these operation signatures. And then a computation type, as I said before, is a pair of this is a value type, ranging over with A, B, etc., and an exception type. Operation, I think the typing rule is pretty obvious. The return type has to correspond to the return type of the operation, and the effect has to allow that operation to be performed. Handlers, you can see it's like a funny kind of application on computations. And then this is the rule that does all the work. I guess a thing to highlight is that with these deep handlers that I'm presenting here, the resumption so we're doing an operation going from A to B, then here's its parameter type, its argument type, here's its result type. But the return type of this resumption is actually D. It's the final computation type of the handler. And that's the thing that encapsulates the fact that the resumption actually recaptures the handler. So the body of the resumption gets handled with the same handler. But yeah, I don't want to dwell on that. I want to show you some more examples. I don't have much time. This example is not that interesting, but I'll quickly show you. So generators. I would say, yeah, the kind of, at least the thing I'm trying to sell effect handlers for mostly at the moment is concurrency and asynchronous programming abstractions. But yeah, generators are something we can implement here. So what's the idea? We could have an operation send. It's going to send a natural number, and then we'll later on say what that means. So this thing we're defining here is a very simple generator that's just going to send a sequence of increasing natural numbers. But then we can define a handler. We can define lots of other handlers to interpret this in different ways. And this handler is just going to it's going to take one of these generator computations and interpret it by reading until it reaches a value stop. And we'll get a list of these natural numbers out. So in the basic case, we get an empty list, and then we just do a check. And if we haven't reached stop, then we output that natural number and then resume. And, well, that's what you expect. But yeah, this is the example I really wanted to show you. I don't really mind if I have to stop before getting much further after this. This is lightweight threads. So a very simple model of cooperative concurrency, where we're going to have a number of different computations, and they all get to perform one operation, yield. It just takes unit to unit. The purpose of yield is not to communicate anything, it's just to say, all right, I'm willing to give up control so another thread can run. And yeah, here's my very simple pair of threads. I'm going to give as an example. And each of them is going to yield once and print out values to sort of checkpoint where we got to. So we want to interleave these two computations. And the point is, we can write a scheduler for this in hardly any code at all, using handlers. Well, okay, maybe it looks a little bit more complicated than we'd like on this version. I have a simpler version we'll get to. But yeah, I'm going to define a couple of types that I need here. So a thread is just a thunk with an effect that's the yield effect. It's an amount of yield. Remember, our resumptions will have handled the yield effect. So we need a type of resumptions. And the resumption type actually has to be recursive because we're going to be passing in the list of other resumptions that we need to be able to resume to. So it's like a thunk, but with this extra bit of state here. And then this is the handler. It takes one of these I'm not sure that this is wrong. That should be it.
Thread E, that arrow rather than one back.
It should just be E union yield here. This one is, this takes a computation that yields. So it should be just the right hand side of here. It should be the type here. And then we're going to interpret that as a function that takes all the other resumptions and then gives us back the unit. Now, the return case, well, we take the list of other resumptions. If it's empty, then we just stop. So this means that the current thread's finished and there are no more threads. If the current thread is finished, then we switch to another thread. And that's it. And the more interesting bit is with yield. So here, well, if there are no other threads, then we just carry on with the continuation again. If there are other threads, then we take the one at the front of the queue and we run that one and we stick our one at the end. And that's it. So that's the handler. For convenience, it's useful to define some little helper functions. This one converts threads, which are the things we actually want to write, into these resumptions. And well, how do you do that? Well, you just handle it with co-op. And then this maps a list of threads. Sorry, this is the thing, the interface we're actually going to want to use here. It takes a list of threads and runs them through this handler. So you just map over lift on those threads, and it's convenient to just use the identity thread as the starting point. It'll immediately stop so that all the other ones can run. And then sure enough, once we've done this, it will interleave these threads. They return the unit, but they also output the print statements we had in V1, V2, V2. So there's print statements, they're kind of external effects, and they work seamlessly with effect handlers. You can mix them in fine. So, questions? And if you're confused, I'll show you 2 more versions of this that get slightly simpler. Oh, no questions. Oh. I thought I got away with it.
What's the difference between effect handlers and first class continuations? It seems like they operate in a kind of similar way.
Well, first class continuations is a rather vague notion. It covers all kinds of things, including this. But delimited continuations, as presented in a standard way, this is just a structured form of delimited continuations.
You'll just take time for another process to do something. You still print it really having so like printing during its short time. Like, why can't you get maybe you can get 81?
No, you can't. Well, it depends on what the semantics is. Assuming that they happen immediately, then it will do this. What I possibly should pointed out will happen. Any operations that are not handled by the handler, so if we view print as an operation, they bubble up through the handler all the way up to the top level. I mean, you don't actually implement that in that way if it's a built-in effect, but semantically you can view it that way. So what will happen is the print will happen, and it's only when it gets to the yield that will get handled by the handler. So that print definitely happens before that yield. And it's definitely going to do this, and then this one yield back to here before anything else will happen. So yeah, you can do that. But we can also plug in other schedulers, any scheduler you like, and run that on the same program. And we can extend it as I would if I had time, but I'm not going to have time, I don't think, to add other features like being able to fork off a process dynamically. So I'll just show you, there's a slight refinement of effect handlers. So it's a bit inconvenient that we had to stick to have the right-hand side here be a lambda like this. And then we had to, and in fact, the implementations can be very inefficient here because it builds up lots of closures. If you just generalize handlers very slightly so that you allow a parameter to be threaded through the handler, so as well as it taking a computation, it also takes this parameter. Then each time you call the resumption, you pass in both the parameter and the return type of the operation, the return value of the operation. Then, well, we've got rid of those lambdas. It's doing the same thing. This is just kind of syntactic sugar. I have gratuitously changed the order of my arguments there, just this. Well, because that was what I had in the rest of the slides. Yeah, and then you can define the operational semantics changes in the obvious way. And the typing rules. I want to show you shallow handlers because this example looks cleaner as shallow handlers. So shallow handlers are very similar to our deep handlers, except the resumption does not wrap the handler around its body, which means you have to do that yourself. But in this case, that made things easier. But the crucial difference you'll see is that this is now, I've defined cooperate directly as a recursive function. With vanilla deep handlers, you build in a structural recursion. You don't need any additional recursion on top of that. So the structural recursion that's built in is this wrapping of the handler around the body. Here, instead, I'm doing it myself. But yeah, the resumption type is just the same as the thread type. And essentially, we're managing this extra state just using a normal binding structure of lambdas. So this is a pretty concise definition. And is it wrong? No, that's right. Okay. Yeah. So all you have to do is
You rewrite the default.
right. This is where we do the analysis that pulls off the thing off the head.
Yeah.
And here we stick it on the end. So that's pretty concise. Yeah. And shadow handlers are convenient, but they can have. So how I think I'm probably out of time, aren't I?
Yeah, roughly.
Guess I'll just state those things about deep handlers. They wrap the body, as I said. Essentially, they perform a fold over the tree structure that's induced by these effects. So if you know about free monads gives you a tree, and it does a fold over that. Shadow ones just do a case split on this computation tree. And then I had a whole load more examples. I showed how you can add fork in one way. Doing it another way. We can do pipes where we have two computations talking to each other. And then I show that you can we can build actors by composing together the lightweight threads handler I showed you with another handler just for actors. Crucially, this one, it takes our actor effect, whatever that was, it had several operations, and interprets it using actually two different kinds of effects. Oh, yeah, this was the lightweight thread effect. So we had fork and yield for the things I had there, and then also some built-in effects. So compose this together very nicely. Here's some programming languages that use effect handlers. I guess I'm going to highlight multi-core OCaml because this is now the next release of OCaml 5, which is going to come out very shortly, actually has effect handlers and a very robust, very efficient implementation of them. Unlike the version I've given, it doesn't yet have an effect type system, which may cause some issues if you try to scale this up. But and then I wanted to finish with this slide. That's the link to my project website and some other resources that are useful. This web page has loads and loads of references, anything to do with effect handlers, including there's lots of libraries and lots of programming languages, and some tutorials that give you more theoretical background on effect handlers and algebraic effects. And Daniel, my student, his PhD thesis, I think is a very good reference for, sorry, I said PhD student, he's my postdoc now, he's graduated. This has lots of good info on what you need to be able to implement effect handlers. So I'm going to stop. But any more questions? Yes.
So sometimes non-tabulation is considered to be an effect. Is it something that you can expect with the effect handler?
Yes. In a sense, yeah. No, that's used very heavily. For instance, so Steve Dancevich and his group have been applying what they call I-trees, which are very similar to effect handlers, but they're co-inductive. And they're using them in Coq for reasoning, for proving properties of programs. And yeah, they make very heavy use of. I mean, the basic idea, one thing you can do is you can just define a recursive function, but replace that recursive function with an operation like this. And then instead of unfolding it by recursing, you can say give it some petrol, some fuel, some gas, And you can say, do this many steps. And you can simulate any number of steps you like in any generally recursive program without actually running it.
Just wanted to hear how do you compare a shadow and deep handling? One prefer over the other?
Right, yeah, there are lots of trade-offs. So deep handling is the pretty thing from the semantic point of view. It's the nice thing. It's also easier to optimize. You can do things like fold fusion with it. But in some cases, it's a bit painful. You can simulate both in terms of one another. If you try and simulate shallow handlers using deep handlers, it's extremely inefficient. You get memory leaks. And there are other variants as well. There's a thing I didn't show you called sheep handlers, which is a hybrid between shallow and deep handlers. So I think, yeah, for some things, shallow handlers are useful. For other things, deep handlers are useful. So maybe you want to support both in a programming language.
Do you know which variant is supported in multiple?
They currently support deep handlers. They will support sheep handlers eventually. So sheep handlers are like shallow handlers, except so they're like shallow handlers in the sense that each time you call the resumption, you can pick a different handler, but you always have to pick some handler. Whereas with shallow handlers, that's done very dynamically. Yeah, also actually we're doing an extension for WebAssembly, and that uses something like these sheep handlers rather than the shallow or the deep ones. Yeah.
We have other effects in core art. We have.
Yeah, I mean, you can. They're expressive enough languages that you can you can certainly simulate something along these lines. I mean, like, and Haskell has many effect handler libraries. The thing that you want ergonomically for supporting a nice effect type system is something like row typing, some form of unordered types. There are ways of encoding a collection of effects types, like as a list, and then saying, oh, but the order doesn't matter. But that can be a pain in practice. So yeah, you can certainly encode them, but there might be something you would want that would be nicer to be built in.
I think there's some meta-theoretical issues with dependent types and effects. And yeah, I think there is a big question on what happens when you parameterize with the computation that does the rest of the weekend that does an operation, right? What does it mean? So.
Yeah. There is, I don't really know anything about it, but there's a theorem proof at Andromeda that Andre Bauer works on that uses effect handlers in its built-in language. Do I see any more questions? No? Okay, well, if you have any more thoughts or questions, then talk to me afterwards or at the barbecue.
All right, thanks, Sam.